Good afternoon, everyone. I'm Le Xianyang from Tsinghua University. It's a pity that I cannot attend in person due to the difficult COVID situation, but I'm happy that I can join this wonderful conference online, and I'm happy to have this chance to present some of our recent results on the electronic structure of the thin films of manganese bismuth telluride. I would like to thank the organizers for the invitation. In this talk, I will first introduce the experimental tool and the research background. Then I'll compare the topological electronic structure of the bulk sample and the thin films. Then I will focus on the observation of the Rashba split band and its interaction with the topological surface states. In the last, I will give a brief summary. Okay, first the introduction. Our experimental tool is the angle-resolved photoemission spectroscopy, APES. The basic working principle is the photoelectric effect explained by Einstein. A photon beam excites electrons out of the solid materials, and an electron analyzer is used to collect the photon electrons, and the analyzer is their momentum and the energy. By simple calculation based on the energy and the momentum conservation laws, we can get the energy momentum distribution information in the solid materials, which is the band structure of the solids. In nowadays, the capability of APES has been greatly improved. By focusing the incident beam down to tenths of nanometer scale, we can measure the local fine electronic structures with micro APES. By attaching the spin detector, we can measure the spin structure with spin APES. If we update the incident beam to pulsed lasers, we can measure the non-equilibrium electronic structure dynamics in time domain using time-resolved APES. Accurate measurements of multi degrees of freedom of quantum materials will provide us more complete information. We use APES to search and study topological quantum materials. Before the discovery of the topological quantum states, the classification of matters was based on Landau's spontaneous symmetry breaking theory. This wonderful picture is challenged by the discovery of quantum Hall state in 1980 by von Kleessen. In the quantum Hall state, the bulk of the state is insulating, but the edge is conducting. Each quantum Hall state can be described by the topological invariant or the chain number. There is no symmetry breaking in this quantum state. Around about 2005, the discovery of the topological insulator further expands the member of topological quantum materials family. Up to date, the family of the topological quantum materials includes many members, such as the topological insulator, Dirac and wire semimetals, and topological superconductors. It's interesting to note that the quantum chemical calculation recently has suggested that more than 70% of crystals are actually topological quantum materials. Our story today starts from the topological insulator. The major difference between the topological insulator and the normal insulator is the inverted band gap and the existence of the topological surface states. In the topological insulator, the strong spin orbit coupling plays a role as the external magnetic field in the quantum Hall state. The spin and the momentum of the surface states are locked, forming a gapless Dirac cone in the bulk gap. Due to this spin momentum locking, the electrons are immune to the backscattering induced by non-magnetic impurities. Therefore, the topological insulator is potentially useful for the low energy consumption electronic devices. In a prototypical topological insulator, such as bismuth telluride, the bulk band topology guarantees the existence of a two-dimensional topological surface state with gapless Dirac dispersion, which can be directly visualized using APES. Time reversal symmetry plays a crucial role in the protection of the gapless Dirac surface state. On the other hand, already from the very beginning of the study of topological insulators, researchers have realized that intriguing quantum phenomena and the new states can be induced if the crucial time reversal symmetry is broken. An exchange gap can be caused in the topological surface state, realizing the so-called magnetic topological insulator. In this situation, a chiral edge mode can emerge with quantized conductivity if the Fermi level is tuned in the exchange gap. Such magnetic topological insulators are potentially useful for engineering a variety of exotic topological magneto-electric effects, such as the quantum anomalous Hall effect, in which the quantized Hall effect occurs without external magnetic field. Another example is the axion insulator phase, in which the gapped surface shows a half quantized anomalous Hall conductivity. By tuning the magnetic structure, other interesting phases can also be realized, such as the Majorana fermions if the superconductivity is involved, or the fractional chain insulators and the wire semimetals. Unfortunately, although the concept is clear and beautiful, it is not easy to realize magnetic topological insulators. Taking the quantum anomalous Hall effect as an example, it was originally realized in vanadium or chromium doped bismuth antimony telluride system. The observation of the quantum anomalous Hall effect requires both fine-tuning of the sample composition and ultra-low temperatures, making the experimental demonstration extremely difficult. It is thus highly desired to search for stoichiometric topological insulators with intrinsic magnetic ordering. In about 2018, the first intrinsic magnetic topological insulator, manganese bismuth telluride, was proposed and ignited intensive research interests. It exhibits a layered structure by stacking van der Waals' septuple layers of manganese bismuth telluride. Each septuple layer can be viewed as an extra manganese telluride layer sandwiched at the middle of the well-known bismuth telluride quintuple layer. It enters an antiferromagnetic ordered state below 25 Kelvin. The antiferromagnetic state ordering is A-type and with the magnetization z-axis along the C direction. Although the anisotropic energy is only 1.7 millielectron volt. Calculation reveals the band inversion near the gamma point with a bulk gap of about 200 millielectron volts, suggesting its topologically non-trivial nature. Correspondingly, calculations predicted a gapped surface state in the A-type antiferromagnetic phase. The surface gap is predicted to be several tenths of a millielectron volt, although it's different in different groups, making manganese bismuth telluride an ideal materials platform to realize quantum anomalous Hall effect. Soon, several remarkable breakthroughs have been experimentally realized in manganese bismuth telluride, including the quantized anomalous Hall effect, even at zero field. A phase transition from a chain insulator to axial insulator to a chain insulator, and the observation of a high chain number chain insulator. We used the APES to study the electronic structure of bulk manganese bismuth telluride. Actually, shortly after the theoretical prediction, many APES results have been presented to show its basic electronic structure. Experiments using synchrotron radiation show a large gap ranging from 50 millielectron volt to 200 millielectron volt, which depends on the photon energy used in the APES experiments. This suggests that the measured band gap is maybe from the bulk bands. Using synchrotron radiation source, we conducted APES measurements at relatively low photon energies. The basic electronic structure is very similar to other reports using synchrotron. We observe a clear photon energy dependence of the dispersion. The valence band top and the conduction band bottom, as well as the gap between them, all show a clear dependence on the photon energy, which is periodically varied. This suggests their bulk origin. Interestingly, at photon energies below 16 electron volt, we observe a weak but resolvable states in the bulk gap, forming a Dirac-like dispersion. This Dirac-like band dispersion show weak photon energy dependence, suggesting its surface origin. In order to understand the nature of this in-gap state, we conducted laser-based APES measurements with superb energy and momentum resolutions. As shown here, we observe a Dirac-like dispersion with diminishing surface gap, which can be better visualized in the zoom-in plot and the second derivative of the spectrum. The topological surface state with diminishing gap was also observed by other groups. At low temperatures, the bulk valence band shows band splitting near the gamma point. And this can be seen from the second derivative of the spectrum, which this splitting disappears at a high temperature above the nil temperature. From the temperature evolution of the EDC, we can see the evolution of this band splitting. This band splitting disappears above 25 Kelvin and suggesting a clear influence of the magnetic ordering in the electronic structure of the system. However, the surface state, this surface state remains gapless above and below the antiferromagnetic ordering, without clear change with the temperature. On the other hand, one can insert bismuth telluride layers between the manganese bismuth telluride layers, so forming other manganese bismuth telluride compounds such as 147, 1610, and so on. The insertion of bismuth telluride layers will suppress the interlayer antiferromagnetic coupling and introduce a ferromagnetic state in the system, which may favor the zero field quantum anomalous Faux effect. We also measured the 147 system. It can be seen as inserting bismuth telluride layer between two manganese bismuth telluride layers. The sample shows antiferromagnetic ordering transition near 12 Kelvin. And it enters a ferromagnetic-like state below 5 Kelvin. Due to the van der Waals coupling between different layers, there exist different sample terminations after cleavage. We can see here from the atomic force microscopy topography. In order to study the surface electronic structure on different terminations, we conducted RPS measurements with high spatial resolution by focusing the light beam into a small spot, smaller than 1 micron in synchrotron radiation and 20 micron in laser RPS. The RPS intensity map on the sample surface indeed show the existence of two kinds of domains with different spectral weight of manganese 3D orbitals. We also observe different core level spectra in these two different domains. We can see a difference from the overall dispersion on the two terminations as well. Here. We then zoom into the spectra near the Fermi level to study the termination dependence of the surface states. Our measurement reveals gapless surface electronic structure on both manganese bismuth telluride termination and bismuth telluride termination. The experiment shows gapless surface state on both terminations, and the overall electronic structures measured is consistent with the calculation, except that the surface electronic structure in the calculation is gapped in manganese bismuth telluride termination. Briefly speaking, the situation in 147 is quite similar to the situation in 124 system. We believe that there is a unified mechanism in the diminishing the surface gap in both materials. The observation of the nearly gapless surface state is beyond expectation, and we haven't fully understood this result. There are many scenarios to explain this observation. I here briefly introduce some of them. Firstly, considering the small magnetic anisotropic energy, there exist multi-magnetic domains of different magnetization orientations on the sample surface. These magnetic domains will mediate the surface state together and contribute to the nearly gapless surface state. The magnetic domains and the domain walls were indeed observed recently by magnetic force microscopy. The size of the domain wall is about 0.5 micron. The other scenario is the disordered magnetization on the sample surface, which recovers the time reversal symmetry and induces the gapless surface state. The third scenario is self-doping effect. Due to the self-doping effect, the gapless surface state is lower in energy than the gapped state. So therefore, this one is easier to be observed. Unfortunately, the true mechanism of the diminishing surface gap is still an open question. To make the situation more complicated, recent RPS measurements suggest the surface gap can vary from 10 millielectron-volt to 70 millielectron-volt, strongly depending on the samples. Some work also suggests the native point defects plays an important role in determining the surface gap. To test these scenarios, we used the laser-based micro RPS to study the electronic structure of manganese bismuth telluride. We built laser-based micro RPS system in our lab. By focusing the 7 eV laser beam down to 1 micro, we can scan in the beam on the sample surface. Therefore, we can measure the intrinsic electronic structure in a single magnetic domain. The scanning photo emission measurement on the striped gold sample shows the spatial resolution of our system to be better than 1 micro. The system also have the capability to measure the spin structure. Using this laser-based micro RPS, we scan the sample surface of manganese bismuth telluride at about 15 Kelvin. Unfortunately, at different sample positions, our measurement did not show a clear change of the band structure, except in the near the edge of the cleaved sample, where the cleavage seems to be bad. The other spectra remain gapless. So it seems that the domain wall is not the major problem for the diminishing surface gap. Further experiments are still going on to study the spatial inhomogeneity of the electronic structure. Okay, next I will talk about the thin films of manganese bismuth telluride 124. In addition to the diminishing surface gap, we noticed several other peculiarities in the electronic structure of manganese bismuth telluride, which were previously ignored. First, there is this kink-like structure in the dispersion of topological surface state. Secondly, the surface state seems to be broadened and weakened as approaching the Fermi level, which is beyond the expectation of Fermi liquid theory. Thirdly, there is Rashba split band, which was attributed to a bulk valence band before. Fourthly, the thin film, which is more important, are still not sufficiently studied. Previous measurements on the film shows a drastic difference between the electronic structures of the films and the bulk. To understand this drastic difference and other peculiarities, we studied the electronic structure of the films using our laser RPS. The films were grown by MBE and were characterized by different techniques. We observe sharp streaks in the read pattern, suggesting the high quality of our samples. The in-plane lattice constant of our crystal is estimated to be 4.3 angstrom, in good coexistence with the bulk sample. The surface topography measured using STM show similar surface structure with bulk sample as well. The hexagonal lattice structure corresponds to the top surface of telluride atoms. Similar to the bulk sample, we also observe considerable defects, mainly from manganese atoms occupying the bismuth sites, or the manganese bismuth anti-site defects. The Fourier transform of the surface map gives an in-plane lattice constant of 4.2 angstrom, consistent with the bulk sample. The MBE grown samples show a high quality. Recently, Professor Kehe's group has successfully observed the quantized anomalous fall effect in the 5SL film. The overall shapes of the rho YX and the rho XX versus H are very similar to those observed in manganese bismuth telluride flex samples that was cleaved. The high field and the low field parts of the curves roughly correspond to the ferromagnetic and antiferromagnetic configurations, respectively. In the ferromagnetic state and high magnetic field, the absolute value of rho yx and rho xx always evolve inversely with magnetic field and with the gate voltage and the temperature, which is a signature of quantum Hall or quantum anomalous Hall effect. The quantum Hall effect is further excluded by the absence of transport features of Landau level formation. Therefore, the high field part of the data are dominated by the quantum anomalous Hall effect. Rho x reaches the quantized value of about 1, nearly 1, below 0.4 Kelvin. Okay, we use laser APS to study the electronic structure of these MBE-grown thin films. We can easily find the drastic difference between the electronic structure of the bulk and the 5SL films. Consistent with the electronic structure of the bulk samples, we observe the conduction band and the valence band with a gap of about 150 millielectron volts. The topological surface state shows a diminishing gap, but no kink-like structure here. It merges into the bulk conduction band with a much weaker spectral weight. The band structure shows a clear dependence on the film thickness. In the 1SL film, we observe an M-like valence band with a band gap as large as 300 millielectron volt between the valence and the conduction bands. Interestingly, the band gap shrinks in the 2SL film and then reopens in the 3SL film. Above the 3SL film, the surface state gradually emerges and finally evolves to the topological surface states in a bulk sample. The experiment is in overall agreement with our DFT calculations. According to the calculation, the topology of the odd number sample films and even number films are different. The even number films are topologically trivial. The chain number is 0. And in the odd number films, the 1SL film is also topologically trivial, but the films are chain insulators in films above 3SL film. Therefore, there is a change of the topology of the films above 3SL.
Excuse me, you have 5 minutes left.
Sorry?
You have 5 minutes left.
I think I have, yes, I will finish in time. We also noticed that the Fermi level of the films is different from the bulk sample. We thus use surface doping of alkali metals to raise the Fermi level of the film. Here is the evolution of the electronic structure of a 6SL film with surface potassium doping. With increasing doping level, the band shifts towards higher binding energies. Interestingly, near 0.1 monolayer coverage, the surface state seems to separate from the bulk states. And the kink-like structure emerges in the surface state, which can be better seen from the second derivative spectrum. This spectrum looks very similar to the spectrum in a bulk sample. The interesting evolution of the band structure induces a Lifshitz transition of the change of the Fermi surface topology from a single circle to 3 circles here, and finally to 1 circle again. Okay, now I will discuss the origin of the kink-like structure. We compare the band structure of doped film and the bulk sample here. Despite the broadened spectra, the basic electronic structures are quite similar to each other, including the kink-like structure, the weakened and broadened topological surface state near the Fermi level, and the emergence of the Rashba split band. The observation suggests that the electronic structure of MBE-grown film is actually quite similar to the bulk sample, except that the doping level and the surface condition may need to be modified. To understand the interesting evolution of the electronic structure, we also conducted a doping-dependent measurement on the bulk sample. With slight doping, the band shifts towards high binding energies. At heavy doping, both the Rashba split and the kink disappears, leaving a band structure similar to that of the thin film. We would like to emphasize that during the surface doping, the Rashba split band and the kink-like structure shift down or up together and disappears at the same doping level of the alkali metals. This lock-in behavior suggests a close relationship between the Rashba split band and the kink. We propose that the kink-like structure is induced by the interaction between the Rashba split band and the topological surface band. In the pristine film, the Rashba split band is unoccupied. With surface potassium doping, it gradually shifts down and hybridizes with the topological surface state, inducing the kink-like structure. At high doping level, both the film and the bulk sample show a similar electronic structure with only inverted bulk band and topological surface state within the bulk gap. The Rashba split band observed in the films and the bulk samples resembles that in the bismuth selenide after surface doping, which is related to the quantum well state formed after surface doping. Based on the 4-band model for topological insulators, we simulated the band structure of manganese bismuth telluride slabs. The surface doping mainly induces surface potential. Without this surface potential, the antiferromagnetic term opens a gap in the surface Dirac cone near the gamma point. When the surface potential is turned on, but the magnetic field is turned off, a quantum well state with Rashba splitting emerges. When both the surface potential and antiferromagnetic term are turned on, the Rashba split band coexists with the gapped topological surface state. Our calculation thus suggests that the observed Rashba split band in the film and the bulk samples are from the quantum confinement effect, similar to the tunable Rashba split band in bismuth selenide. The observation of the Rashba split band and its interaction with the topological surface state is not trivial. First, it will contribute to significant carriers to the system, which will play a role in the transport of the material. Secondly, it provides a platform to realize the Rashba ferromagnet, considering the surface ferromagnet of the sample. As proposed by the theory, the spin-optic coupling and ferromagnetism may open a gap at the band crossing point. Such a system is attractive for the anomalous Hall effect and possibly also for quantum anomalous Hall effect. Okay, I would like to summarize my results with these two videos. We reveal a topological phase change from a trivial band insulator in 1 SL film to a chain insulator in 3 SL film. We observe a Rashba split band interacting with the topological surface state in manganese bismuth telluride, which induces the kink-like structure. The surface states can be effectively manipulated by surface potassium doping, and the Rashba split band may establish a Rashba ferromagnet on the surface of the sample. Okay, I would like to thank my collaborators. The films were grown by Professor Kerher's group, and the bulk samples were grown by Professor Wang and Professor Guo. And APES measurement were conducted in Tsinghua University with help from Professor Yulin Chen and Zhongkai Liu's group. The calculation was done by Professor Xu Yun in Tsinghua University. Okay, thank you very much.
Okay, thank you very much. A wonderful talk. Well, is there one urgent question, please?
Thank you very much for the nice talk. I have a question concerning this Rashba state. Why would there be the Rashba state on the surface of the bulk single crystal of MBT without any potassium deposition, on your opinion?
Yes, I think a possible reason is due to the defects, which induces additional carriers on the surface. It's similar to the potassium doping.
What kind of defects that would be different from those that are already present in the bulk? You just cleave the bulk single crystals, the defects will be just there in the surface subtopo layer, which would be exposed by the cleavage. And so
Yes,
where
then
does
this, but the surface is always not ideal. It's there is a manganese bismuth andesite defects which can induce electrons or let's say carriers, which can induce the quantum confinement effects.
So you think they appear at the surface more than in the bulk? In the block
Yes.
layer at van der Waals material, which is like chemically
Yes.
inert and protected and stuff.
Yes.
Okay, thanks.
Okay, our time came to end, so let's thank all the speakers of our session once again.